Okay. Good morning, one and all. On behalf of KSTA and on behalf of Surana Group of Institutions, a warm welcome to everyone and a special welcome to distinguished speaker for the day, Dr. Krishnendu Gangopadhyay, respected Dr. A.M. Ramesh sir, CEO, KSTA, and respected Dr. P.M. Patil sir, participants and dear colleagues. I would like to give a brief introduction of the speaker, Dr. Krishnendu Upadhyay sir. He is working as an associate professor at IISER, Mohali. His area of specialization is in hyperbolic geometry and group theory. He has published many research papers and at national and international levels, and he has guided many doctor theses and 15 master theses, and he has guided several external and internal summer students, and he is appointed as an adjunct faculty of the Center of Excellence in Mathematical Sciences, and he has been invited for many conference talks and at national and international levels. With this brief introduction, I'll welcome you once again, sir, for the day 3 of Srinivasa Ramanujan Memorial Lecture Series. Thanking you, sir. It's over to you, sir.
Sir, you are on mute, sir. Sir, you are on mute, sir.
You unmute it.
Hello.
Oh, I am not understanding.
No, sir. Please go ahead, sir.
Then?
Now we can see your presentation also. Please open the PDF, sir.
Yes, I am unmute.
Yeah, we can hear you, sir.
Yeah.
Please go ahead, sir.
Yeah. So now,
Yes, sir.
right?
All well, sir. Please go
You
ahead.
can hear me properly.
Yes, sir.
Okay, all well.
Yes.
Okay, so this is a new system that I am lecturing for the first time. So it was a kind of experience, good experience to try different online teaching tools that we are usually familiar with. So normally I use Zoom or Google Meet, but this system is something new. So it took me some time to get adjusted with it. But now I hope we are all set and I can start my lecture. So as you can see, as I think Professor Ponnusamy and Professor Ramesh and other people pointed me out that this is a workshop meant for undergraduate and college students. So I have made my lecture a very sort of elementary so that I can workshop. Instead of talking about something very technical, I thought I will I shall tell you a story about the logo of the ICM 2010. Now, what is ICM 2010? So the ICM means International Congress of Mathematicians. So the International Congress of Mathematicians is the largest conference in mathematics. It's a very large and it's an international conference where people from each part of the world takes part. Now the ICM takes like Olympic Games, like once in every 4 years. Was held in Zurich in August 1897. So around the same time when Olympic Games were probably also started. Now in mathematics there are, two awards which are highly prestigious. I think you must be knowing that in mathematics there is no Nobel Prize, but there are equivalent prestige that is given to mathematicians. Now the oldest one is called the highest honors for a mathematician. But there is a catch. The mathematician has to be under age 40 to receive this award. So I hope some of the young people will be inspired to become mathematicians and will do excellent work so that they can at least understand some of the work that Fields medalists are doing. Or I hope some of them will also be eligible for such award one day. The other award is called Abel Prize, not Nobel, but Abel Prize. There is no upper age limit. But since we are, but the Abel Prize is given in some other program in Norway, but the Fields Medal is given in this meeting called the International Congress of Mathematicians. And even if someone is invited for a talk in this conference, that is also considered to be a very big prestige for a mathematician. So it is indeed a very important conference in mathematics, and it's an experience to take part in such a conference. Now I had the privilege to attend this one and the other one in 2006. After that, I did not have much time to go there, but I hope I will attend the next one in due course. Now, I hope I have been able to convince you that the ICM is undoubtedly the most important conference in mathematics, and in India, it took place in 2010. This was, of course, the first time that it took place in India. But if you go beyond India and look at from a global perspective, ICM 2010 that happened in Hyderabad was only the third time that this event took place in Asia. Most of the other events will take part in several parts of the Europe. But in India, it was for the first time in 2010. And it was, I think, our colleagues see this conference. It was a very big event. But what we are interested in this talk is the logo of the ICM 2010. So here is the logo of ICM 2010. It's a nice symmetric picture where ICM 2010 is written here. And in the bottom, there is a Sanskrit sloka. May good ideas now, because this formula, this means something. This chair of Ramanujan. And
Sir,
for a long time.
Sorry to interrupt, sir. There is a bandwidth issue, I think, at your end.
Yeah.
Yeah, I think better to stop video and continue.
Let me just resolve it.
Continue, sir, please. I will just intimate you if there is a problem.
I mean, you please do intimate me whenever there is a problem, because when I am lecturing online, I think you have to interrupt me.
Yes, sir.
Otherwise, I will not know what is happening here.
Sure, sir, sure.
Okay, so this this formula, this inequality, this was. I will explain towards the end what does this inequality means. But this was a very long-standing conjecture, and it was solved by Pierre Delin only in 1978. And Pierre Delin got the Fields Medal for solving this conjecture. So you can understand that it was in. the first design was done by one colleague, one mathematician called Pablo R.S. Gastesi, and the final version was done by Ms. Minal Designs, Mumbai. Do here is to tell you about what is the mathematics behind this logo. Am I audible or visible? I suddenly
Yes, sir.
realized that there is some issue.
Audible, sir. Audible, sir.
Yeah,
Audible,
okay. But not visible, yeah?
Video, your
Because
video, I
can
have
see my
turned it off, sir.
video.
Bandwidth, it will take lot.
Oh, okay,
But
fine,
presentation is off.
perfect,
Presentation is
no
visible.
problem.
Yes.
Okay, perfect. Okay.
Yes.
So, we will discuss what is the geometric meaning of this picture and the formula, the mathematics behind this logo. Now, to understand the mathematics behind this logo, we need to learn some geometry. Now, first, I will recall our school geometry. That is good to revise. Now, you might remember that in our classical school geometry or the Euclidean geometry, it was based on 5 postulates. And based on those 5 postulates, we developed several theorems. Now, the first postulate was that there exists a line between 2 points. Given a line, there is at most 3 points. There are at least 3 points outside it. 2 lines are either intersect, and if they don't intersect, we call them parallel. Now, there is this concept of a point and a circle. Given a point and a radius, we can draw a circle. There is a concept of angle, and there is this parallel postulate. Given a line L and a point P not in the line L, there exists a unique line passing through the point outside L and parallel to it. So this is called parallel postulate of Euclidean geometry, and this defines Euclidean geometry. Now, for a curious mind, one can always ask, what would happen if we don't have one of these postulates satisfied? Now, or how can we minimize the number of postulates? So for 1,000 years, mathematicians tried to prove this parallel postulate by the other postulates, and they failed. Then they thought that what about if we don't assume parallel postulate? What will it give? So that's what we will discuss. Now, based on
Sir, we have lost you, sir. Krishnendu, sir, can you hear me?
yeah, I can hear you. Can you hear me?
Yes, sir. Yes, sir. Please go ahead, sir.
Yeah. Okay, just a minute. Maybe I move to a place where I have better Wi-Fi connectivity. Okay, so I hope I am audible now properly. Hello, Ramesh, are you there?
Yes, sir. Yes, sir.
Okay. All right. So we have this of several triangles, and it's a kind of well-known result in Euclidean geometry that the sum of the angles of a triangle is 180 degree, and then you can define several angles and several theorems regarding all these things, and all this axiomatic formulation can be made precise by the concept of a metric that we will come shortly. But now, as I mentioned, that people attempted to prove Euclid's this parallel postulate from the other four and they failed. So they ask, what about given a line L and a point not on it? There is more than one line going through the given point and parallel to the given line. Does it define some geometry? The answer turns out to be yes. If you replace fifth postulate by this one, with the remaining four as it is, one has a new kind of geometry called the non-Euclidean geometry. And you can exactly the same way you have developed school geometry. If you keep the other postulate same and replace the parallel postulate by this one written in red color, you can develop several theorems and several properties of the Euclidean of the geometric space, which is not exactly like Euclidean geometry, but somewhat similar and somewhat interesting in its own spirit. It turns out that lines cannot be any more straight lines that we have in our mind when we do geometry, but lines will be curved. And some of the angles of a triangle in this sort of geometry is not pi. All right. And there are names like Gauss, Lobachevsky, Bolai, Poincaré, who are all pioneers to develop this sort of geometry. Now, broadly speaking, you can divide the entire class of geometries into three types. One is Euclidean, where our triangles are such that the sum of the angles is pi, and the other two are spherical, where triangles are thick, sum of the triangles are greater than pi, and hyperbolic, where triangles are thin, that means sum of the angles of the triangle is less than pi. Now this characterizes these three special geometries that we can build from a piece of paper. And as you can see that the sum of the angles of the triangle characterizes it. Now these were all axiomatic. Now what we want to make it more precise in mathematics. Now for that we need to build up analytic models for geometry. Now let's recall the analytic model for Euclidean geometry. That is the high school geometry that we have learned in terms of coordinates. We call it coordinate geometry. So what we did, we take R2, which is a piece of paper. We mark a point as origin, and we take two perpendicular lines, x-axis, y-axis. That gives us the model. And then what we did, if you marked this point origin on the xy plane, then that's a vector space. But on a piece of paper, we want to draw a line everywhere. So we will forget this origin and we will draw our line and triangles everywhere on the plane. And R2, if you forget the origin, is called an affine space, and we denote it by A2. So A2 has no mark point like origin, but you can draw lines and circles everywhere on the piece of paper. And arithmetically, when you take two tuples of point x1, y1, x2, y2, their sum is still a well-defined concept. And go back to the underlying vector space. You can take two vectors, x and y. You can always talk about their sum and differences. That gives you the concept of a metric, which is the Euclidean metric written here, d x1, y1, x2, y2, the usual metric. And R2 A2 equipped with this metric is a model for our Euclidean plane. And all these axioms that we discussed at the beginning can be made precise using this metric. Now, what I will appeal now is not the detailed formulation, but the concept of Euclidean arc length that you must have also seen in your high school or beginning undergraduate courses. That when you take a curve gamma joining 2 points, say you are taking the curve from A to B, then you can measure the length of the curve. What you do, you just integrate the derivative of the curved from A to B, and we call that length of a curve. Now, among all the curves joining these 2 points on Euclidean plane, there is a unique curve that minimizes the length, and that is straight. That's our straight line, right? So along the straight line, the distance between 2 points is achieved. That's the minimum length among all the curves joining these 2 points A and B, and that's exactly the distance between 2 points A and B with respect to the Euclidean metric. So keep this picture in mind in what follows, because we will exactly mimic these ideas, but we will scale our length. So, and that will give us hyperbolic geometry. I will not discuss spherical geometry here, because for us, what is interesting is hyperbolic geometry, which will tell you the meaning of the ICM 2010 logo. So I hope everybody is familiar with complex numbers here. Now, complex numbers will play handy to understand the meaning of the ICM logo. So what you do, you start with the complex upper half space. Okay, not the whole complex plane, but the complex upper half space where imaginary part of y is always positive. Now you scale the Euclidean arc length by imaginary part of z. So call it ds, which is exactly mod dz by imaginary part of z. Then, just like you define the length of a path, you define length of a path gamma from between 2 points A and B to be the integration of this arc length. Okay, so this is a new infinitesimal length that we have, and we will work with it. Now, if there is a path which minimizes the length between 2 points, we will call that a line in this geometry. And in a more fancy terminology, these are called geodesics. We can call them hyperbolic line to distinguish them from the Euclidean lines, which are the straight lines. Now the hyperbolic metric, like previous, is the infimum of all the lengths between z and w along curves. Now you can check that this gives you a metric in the metric space sense, and I denote that metric by rho, and this formula gives you an expression for the hyperbolic metric. You see, it's slightly different from this mod z minus w. That is the Euclidean metric. So what you are doing, you are essentially scaling the Euclidean metric nicely, and then translating it by 1 to sort of get expression for the hyperbolic metric. Now, the upper plane equipped with this metric rho is called the upper plane model of the hyperbolic plane. An isometry of hyperbolic plane is a distance preserving bijection, a map, bijective map that preserves the distance rho. We also have the concept of isometry in Euclidean plane, which you probably have learned as rigid motions of the plane. So they are essentially the isometries. I will not speak about that in detail, but for us, a isometry of the hyperbolic plane is a distance preserving bijection, which satisfy this equation, this formula. Like, it does not change the distance. That's the isometries. Now, what are the lines in H2? So you start with a vertical line, all right? You take a vertical line where your x naught is always 0, x coordinate is always 0 in the complex plane, okay? You compute the length of the vertical line, which is log y1 upon y naught. Now you take any other curve joining these 2 points p naught and p1 on a vertical line. Whatever curve gamma 1 you choose, it will always have length greater than or equal to the length along p0 to p1 along the vertical axis, right? So that means what? Vertical lines are geodesic, because vertical lines are the curves where the length is minimized between 2 points on the vertical line P0 and P1. So they are geodesics. So it's a nice information. So vertical lines are hyperbolic lines. So we in Euclidean plane we have straight lines. Here also we have vertical lines which are straight in the Euclidean sense, but they are hyperbolic lines. What about others? Are they all? They are not all. We still have more family of geodesics or hyperbolic lines. But to find out, let's find out some tools that will transfer one geodesic to the other. What are those tools? Those are the isometries. So let's find out some isometries. Now you recall mirror reflection in a line in the Euclidean plane. Z goes to Z bar, the complex conjugation. And so where B goes to the mirror image of B, and that's the mirror reflection. So this is a very well-known isometry of Euclidean plane. Now in hyperbolic plane, we want to define something like this, some sort of reflection that will generalize the mirror reflections in the Euclidean plane. Now how do you do that? For that we will again recall one picture here. So you have a circle here with center A and radius R. Take a point inside the circle, Z. What you do, you draw a perpendicular through Z, which will hit the circle at exactly 2 points, U and B. Draw tangent, one from U, one from B, and take their intersection points. You will see that these tangent lines will intersect the long line that joins A and Z. It intersects at the point Z prime. This gives you a function which fixes the boundary of the circle, takes insides of the circle outside, and outside of the circle inside. And this sort of transformation is called an inversion. Now, if you take a circle of center 0 and radius 1, then inversion in a circle is given by this formula, sigma z equal to 1 by z bar. Okay. So, you see that the inversion has these nice properties that it's an order 2 transformation. That means just like reflections, sigma square is identity, and for all points on the unit circle, sigma fixes every point on the unit circle. All right. And it is easy to check that sigma restricts to an isometry of H2. So you just plug in the value of sigma in the formula of the length. You will see that d sigma z by imaginary of sigma z is equal to mod dz by imaginary z. That proves that the inversion in S0, 1, the circle of center 0, radius 1, is an isometry of the hyperbolic plane. Now let's find out some more isometries. It's easy to see that if you take this transformation, the Euclidean rigid motions of the form A plus Rz, where A is a real number, R is a real number, then that is also an isometry. It's very easy to check. And you take any other circle of center A and radius R, then inversion in SA, R is a conjugate of sigma by these transformations phi. So phi, sigma, phi inverse. And since we can, I am assuming here that you take the set of all isometries, they form a group. So phi, sigma, phi inverse are also isometries. So inversion maps are isometries of the hyperbolic plane. Now, where does inversions map vertical lines? The inversions will map vertical lines onto semicircles in H2 whose center lie on the real axis. Thus, semicircles orthogonal to the real axis are also geodesics in H2. Now, a geodesics or a hyperbolic line, now are they all? They are all, and it's a fact that you take any hyperbolic line that is either a straight line or a semicircle orthogonal to the real axis. That means either they are vertical line or they are semicircle orthogonal to the real line, and it's very easy to prove. Again, the proof is pretty elementary geometric proof. So you suppose there is a geodesic gamma that is not of these two types. So what you do, you choose 2 points P and Q on gamma. Now, by our classical ruler and compass construction, if P and Q are vertical, then we get a vertical line. If they are not vertical, you join them by a line PQ and then take the perpendicular bisector which hits the real line at the point C. Now the circle, center at C and radius CP will pass through P and Q, and it will be orthogonal to the real line. So by our previous knowledge, it is a geodesic. Now, we have already seen that when there is a length minimizing curve passing through 2 points, there cannot be any other length minimizing curves. So this proves that a geodesic of a hyperbolic plane or a hyperbolic line is either a straight line or a semicircle orthogonal to the real line. So this gives you a description of all hyperbolic lines in hyperbolic geometry in a precise way. Now let's come back to the logo again. You see, okay, let's come back to the logo. Let me zoom in for your convenience. In this logo, what this picture represents, it represents a section of the upper half's hyperbolic plane. All right, and these circular lines, they are sectional view of geodesics. Now you see this hyperbolic line gamma 6. You take the hyperbolic line here, gamma 6, and take a point P, which is not on this line. Now there are this gamma 1, gamma 2. These two lines, they are not intersecting gamma 6, but both of them are passing through P. That means what? You take a hyperbolic line gamma 6 and a point P not on gamma 6. There are hyperbolic lines which are disjoint from gamma 6. That's a parallel postulate. So there are more lines which are parallel to P, parallel to gamma 6 and passing through P. All right. So this violates the Euclid's fifth postulate, and it satisfies the postulate that I mentioned in red letters earlier. So this is indeed giving us a model for the hyperbolic non-Euclidean geometry. All right, and this, so we understood part of this picture. What is the space where these nice symmetries are taking place? But do we understand the entire picture? Not yet. There are more symmetries hidden in this picture. Now, what do I mean by symmetry? Now, given a geometric space, symmetry is a function that preserves geometric properties. Like in Euclidean geometry, deflection is a symmetry. So essentially, what I mean by symmetry are the isometry. Now, what were the symmetries in Euclidean geometry? As I mentioned earlier, they were the group of rigid motions. If you use complex coordinates, then essentially they are these maps. Z goes to Az plus B or Z goes to Az bar plus B. So these are the maps which were symmetries of the Euclidean geometry. And the same question we can ask here. What are the symmetries of the hyperbolic plane? We know what are the geodesics of the hyperbolic plane. And we know that symmetries or isometries of a hyperbolic plane maps geodesics onto geodesics. We have seen some of the symmetries already, which are the inversions and these transformations of the form A plus RZ, where A and R are real numbers. What are others? Here we go to find out the other symmetries of the hyperbolic plane. Now, as I have mentioned, we have already seen z goes to 1 by z bar and z goes to a plus rz are isometries. You can easily check. Z goes to minus z bar is also an isometry of the hyperbolic plane. Now, composition of two isometries is again an isometry. So, the inverses of all these transformations, they are also isometries. Now, if you compose all these transformations, you will see that this Mobius transformation, z goes to az plus b by cz plus d, or z goes to az bar plus b by cz bar plus d, with the condition that a, b, c, d are real numbers and ad minus bc is either positive or negative. They are also isometries of hyperbolic plane. Now, with little bit more work, we can actually prove that these are all. There cannot be any other isometry of the hyperbolic plane, and these are all the isometries of the hyperbolic plane. And they form, two disjoint subsets of the hyperbolic plane. If you know group theory, then one component like the isometry plus, isometry not, or isometry minus, I mean, they give you a coset decomposition of the isometric group of the hyperbolic plane. Now, the elements of the form z goes to az plus b by cz plus d, they are, they preserve the orientation. I mean, if you follow along a direction in a path, these isometries will preserve the same orientation. But when you take bar, they reverses the orientation. All right, and the identity map, the identity isometry belongs to this isometry not H2. Okay. Now, so far what we have done were pure elementary complex analysis and elementary analysis. All right. Now, there is a group involved here. Let's find out that the isometric group is there. Now, can we identify it with a group which we already know well? Well, you take the Mobius transformation, z goes to az plus b by cz plus d. You see, if you replace a, b, c, d by a scalar multiple, they cancel out and you get the same transformation. So that means az plus b by cz plus d are in bijection with 2 by 2 matrices a, b, c, d. Again, if you scale it by the determinant, then you can map it to a matrix A1 whose determinant is 1. So, if you mod out the 2 by 2 invertible matrices over real numbers by scalar matrices that precisely have bijection with isometry H2, and it will be isomorphism, group isomorphism. And the component isometry not H2 will have bijection with SL2R, the group of 2 by 2 real matrices with determinant 1 modulo the plus minus identity. And we denote that group, that quotient group SL2R mod plus minus identity by PSL2R. So here we see a nice information that the isometric group of the, orientation preserving isometric group of the hyperbolic plane that identifies with a group we know very well. That's the 2 by 2 matrix group. So probably we can use linear algebraic tools also to understand geometry of the hyperbolic plane, and we can indeed do that. All right. Not only linear algebra, we can also use more sophisticated tools to understand the geometry in terms of group actions. All right. Now the group SL2R indeed acts nicely on hyperbolic plane, and this action is homogeneous. That means it's like affine space with respect to this group. So you take any 2 points on the hyperbolic plane, you always get an isometry that will map one point to the other. So if you look from the scene, which are isometries, any 2 points look very similar. As far as isometric group action is concerned, there is no mark point, all are equal. And such a space is called a homogeneous space. Now, the action also preserves the boundary of the hyperbolic plane. Now, so far we have not talked about the boundary of the hyperbolic plane, but if you see the upper half space model, you always have this real line, which is like the boundary, which is the boundary of the upper half plane. And the isometric group acts very strongly on the boundary. So it maps any triple of points to any other triple of points. All right. Now we just talk about boundary. Now, what is boundary here and how the hyperbolic metric behaves near the boundary? Now, you see, now I recall a old exercise from your complex analysis course. In complex analysis, you must be encountering Mobius transformation. Z goes to AZ plus B by CZ plus D, where A, B, C, D are complex numbers. Now, when does it preserve the extended real line? It's an exercise that it preserves the extended real line if and only if A, B, C, D are real numbers. Now, if there are college students here, I would like to ask, how did you prove it? I mean, you must have used some tool, right? And the tool was kind of cross ratios that can be used to prove this exercise. But this exercise may also be thought of as a starting point of everything that I have said. All right. Now, I am talking about extended real line, which means I am taking the real line and adjoining infinity to it, because you see when Z equal to minus D by C, this Mobius transformation maps minus D by C to infinity. So if I want to have a nice 1, 1, 1, 2 bijection, instead of only the real line, I will talk about the extended real line by adjoining infinity. Now, does that mean that H2 is bounded by a circle? Because R union infinity, the extended real line, is a circle. You can see it by stereographic projection. If you take the extended complex plane, that's a sphere, and the real line along with that point infinity is a circle along the diameter, right? Circle on the sphere. So that means H2, though we saw on the ICM logo or on the formulation that I have described, though we thought it's the upper half plane, but it looks like it is bounded by a circle. So that means it's something like a disk. And it is indeed the case. You can easily see it. If you take this Mobius transformation, Z goes to Z minus I by Z plus I, you will see that it maps the upper half plane biholomorphically onto the unit disk. Now, when it maps upper half plane biholomorphically onto the unit disk, by continuity, it maps the boundary of the upper half plane, the boundary of the unit disk. So it maps the boundary of the upper half plane to the circle. So this gives us a more familiar model for the hyperbolic plane. So what we were thinking as something very unbounded, it is not that. We were only looking at a section. We cannot see infinity with blind eye. But when you use special spec, you can see the infinity, and from the top, you see that the hyperbolic plane, the upper plane, is nothing but the unit disk. And why? And this boundary, the boundary circle, we call it boundary at infinity of H2. So in Euclidean plane, when you take two parallel lines, what you say? That they intersect at infinity, right? Now, here, you see, there are several parallel lines, and all of them as endpoints on the boundary circle, right? So parallel lines intersect at the bounds, like this gamma 2 and gamma 3. They are parallel lines because they don't intersect in the hyperbolic plane, but they intersect on the real line. And you can also check that if you take this hyperbolic arc length, you see it is scaled out by 1 by imaginary part of Z. Now, as you approach Z along the real line, imaginary part of Z becomes 0, right? So the length is also becoming larger and larger. So it's indeed we are approaching towards infinity when we approach towards the boundary circle. And for this reason, the real line along with infinity is called boundary and infinity of the hyperbolic plane. Okay? Yeah. So this is a picture of the entire hyperbolic plane, the disk model, using that Mobius transformation. Now, in this picture, we see that the hyperbolic plane has been tessellated. I will come. What does it mean? So tessellation, you take it in, in linguistic term at the moment. So it is covered by hyperbolic triangles. You see, there are this big triangle in the middle, and there are these smaller triangles. And some of the triangles in this picture, especially this smaller one, they all have their, they have at least 2 of their vertices on the boundary, or one of their vertices on the boundary circle. So, yeah. So this gives a nice picture of the hyperbolic plane tessellated by hyperbolic triangles. And from this picture itself, you can see if you take the 3 angles of a triangle, then their sum is less than pi, because you can imagine one Euclidean triangle along these 3 points, and definitely this sum of these angles will be less than the sum of the angles of the Euclidean triangle. So it's less than pi. But this gives you a global view of the hyperbolic plane along with its boundary at infinity. So even though it was seemingly like a half of the complex plane, which in our mental setup looks very big, but is actually very bounded, provided you include the boundary at infinity. And you can approach infinity in all directions at the hyperbolic plane. So it's indeed a nice space and pretty much different from the Euclidean plane. All right. So, but does that all about our ICM logo? No, we still have something more in it. All right. So what are the geometric objects that is associated to the ICM logo? Okay. All right. So the geometric objects that is associated with the ICM logo are discrete subgroups of the isometric group. Now, a subgroup gamma of PSL2R is discrete if the, what is PSL2R? PSL2R is the 2 by 2 matrix of the determinant of 1 that is contained inside R4, right? So there is a topology, natural topology on PSL2R. And if you take a subgroup gamma of PSL2R, the induced topology is the discrete topology. We call that discrete subgroup. All right. Now, you can prove that a subgroup of PSL2R is discrete if and only if, whenever you have a sequence of isometries approaches to the identity, everything is identity for sufficiently large n. That's the concept of discreteness. All right. Now, in case of hyperbolic plane for PSL2R, we have something more. We can actually find out the discreteness by looking at the orbits. So let gamma is a subgroup of PSL2R, then gamma is discrete if and only if for all points on the hyperbolic plane, the orbits are discrete subsets of the hyperbolic plane. So to find out the discreteness of a subgroup, we don't look at the subgroup at all. We just pick up one point from the hyperbolic plane, look at its orbit. If the orbit is discrete, we can immediately say that the subgroup is discrete also. Now the action of discrete subgroups of PSL2R is encoded on the gamma action on a smaller region of H2. This is an indication that we don't have, if we want to find out the action of discrete subgroup of PSL2R, we don't have to look at the entire action of gamma on the hyperbolic plane. There are smaller region of the hyperbolic plane that is enough to study the action of gamma onto itself. And such a region is called a fundamental region for gamma. Now, a closed region of the hyperbolic plane is defined to be a fundamental region for the subgroup gamma if the orbit of f by gamma covers the whole hyperbolic plane and the interior of f and any of its orbit are empty. All right. If these two properties are satisfied, then the family, the orbit of f is a tessellation of H2, and the region f, region in a complex plane means open connected subset, right? So the region f is called a fundamental region for gamma. And it's a important fact that you take any discrete subgroup of PSL2R that will possesses nice fundamental domains. So that means every discrete subgroup of PSL2R has a fundamental domain that encodes the action and the geometry of the entire geometry of the subgroup action of the subgroup action on the entire space. So you don't have to look at the action of gamma on the entire hyperbolic plane. You can just restrict it over the fundamental region. All right, and topologically, it's a very important region because of some fact that you take any compact connected surface in our universe, then that can be realized as a quotient of the hyperbolic plane by this discrete subgroup action. And it turns out that that is the same as the quotient of the fundamental region modulo this discrete subgroup action. I will not speak much about that in this talk because my aim here is to explain you the ICM logo. So for that, I will give you an example of fundamental region. So to construct a fundamental region, what you do, you start with a discrete subgroup and you take a point on the hyperbolic plane that is not fixed by any point other than the identity of gamma. Then you take these half planes, dp of gamma, right? The half planes. Now you see, if you have a point P and you take its image under a element of gamma GP, then this geodesic join, any 2 points on the hyperbolic plane can be joined by a geodesic. You join P and GP by a geodesic. All right. Then you take the perpendicular bisector with respect to the hyperbolic metric of this geodesic. Now, 1/2 of this perpendicular bisector is this space HPG. Okay. Okay. This space HPG, and the fundamental region of gamma is intersection of all such half spaces. So dp of gamma is the intersection of all such half spaces by gamma. All right, and you can, it is possible to prove mathematically that this dp gamma is indeed a connected fundamental region for any discrete subgroup of gamma. If you construct it by that way. Now, what is a standard example of a discrete subgroup of PSL2R? It is the 2x2 matrices over the integers, which is PSL2Z. That means you take the 2x2 matrices of determinant 1 over the integers, take its quotient by plus minus identity. This is a discrete subgroup of PSL2R, and this picture, this shaded region, which is bounded by these two vertical lines from -1/2 and 1/2, and this region, this is the fundamental domain for PSL2Z. All right, And this is the Dirichlet fundamental domain of PSL2Z. So it is essentially you take part of this circle centered at 0 and radius 1. So you take this circle and take this. So you see this this shaded region. You can think of it as a triangle where there are two vertices here. One is here, and sorry, there are two vertices on this circle, and the third vertex is at infinity, right? So this triangle with one point at infinity is the Dirichlet fundamental region for PSL2Z. Now let's come back to the ICM logo again. You see this logo now, probably if you compare this logo with this picture, you will see that actually this logo represents only this section, this shaded section of this picture, which is the Dirichlet fundamental region for PSL2Z action on the hyperbolic plane. Now, PSL2Z classically is called the modular group, which is important if you look at it from a number theoretic viewpoint. This function tau of n, it is Ramanujan's tau function, and it is given by this modular discriminant function delta. So delta, if you apply delta on this Az plus b by Cz plus d, then it satisfies this equation. So it is equal. This delta applied to this fraction is equal to Cz plus d to the power 12 times delta of z. Such a function is called modular discriminant, and there is a series which is called modular, which is called Ramanujan's tau function that is related to this modular discriminant, and Ramanujan's tau function and this modular discriminant are related to the concept of the hyperbolic plane by this group PSL2Z. Dn is the number of divisors of n. All right. So if you take n prime, then this formula takes the simpler form. Mod of tau n is less or equal to 2n to the power 11 by 2. All right. So this is the exact meaning of the hyperbolic of the logo of the ICM 2010. So the logo of the ICM 2010 gives you the Dirichlet fundamental region of SL2Z action. So what is the Dirichlet fundamental region here? All right. So in the ICM logo, the ICM 2010, this light yellow shaded region is the Dirichlet fundamental domain of the hyperbolic plane. And below the Dirichlet fundamental domain, the domain you have that is tessellated by several hyperbolic triangles. Now, on this boundary, you have these small shaded triangles, shaded geodesics, you can say, right? These geodesics, the small shaded geodesics. So, what does it mean? I mean, these also has some meaning in terms of, Cantor sets. So this is another object that is related to it. I will not discuss that here, but this also has some meaning which I skip here. But I hope I have been able to tell you that this upper yellow shaded region is the Dirichlet fundamental domain. This is the Ramanujan function related to these divisors. And below this circle, this region, this minus half to half, this region has been tessellated by several hyperbolic triangles, or several geodesics, several regions bounded by the geodesics, which all are starting from this point, and the other point is not seen in this picture. So this is the exact meaning of the ICM 2010 logo. Though it's a nice picture, but there are lots of deep mathematics inherited or implicit in this picture, encoded in this picture. There are lots of deep mathematics encoded in this picture, and this conjecture by Ramanujan, it was an extremely hard conjecture, and Pierre Delin uses lots of deep tools to prove this conjecture. And it's a highly non-trivial work, as I have mentioned, because it got Fields Medal for this work, and many more works, but it's indeed a very deep mathematics that is encoded in this picture in front of you. And what I have given here is just to make an attempt to, tell you some of the mathematics which are easy to communicate. And I hope I have